In the previous lecture, we finished chapter 5. We now have chapter 6, which is about line integrals. It's about line integrals. In this chapter, we have line integrals of scalar fields, line integrals of vector fields, conservative vector field, and also Green's theorem. Here, totally in this chapter, we talk about how to find the line integral. First, we have line integrals in scalar fields. We say for the curves on xy plane, that means if we have a function of one variable, we say given a curve C as y to be f of x. This is the curve which is given from point A to point B. Then the arc length from A to B over this function, over this curve. Here, let's say this is a point, this point A, and this is point B. This is the curve. This is curve C. The length of this curve, the arc length from A to B over this curve, can be obtained by this rule. We say it is the integration from x0 to xn for dy over dx squared. Here we take the derivative for the curve with respect to x, then squared plus 1 all dx. Here we find the integration for this square root. In the square root we have dy by dx squared plus 1 with respect to x from x0 to xn. This is the length of this arc from A to B. Okay, and also if we have a function g of xy over the curve, to find the integration for this, function g of xy over the curve C, we say it is the integration from x0 to xn for g of x and f of x. Here we must change y to x in the function. The function is g of x and y. We have x and y, but y is f of x. Y is given above. It's a function of x. We replace y by the function. Then we get only a function of x. It's g of x and f of x. Then times the integration of dy by dx squared. Sorry, the square root of dy by dx squared plus 1 all dx. Here we find the integration for this formula. G of x and f of x times the square root of dy by dx squared plus 1. We find the integration for this formula from x0 to xn. Here we have just the rules. If you have a curve x to be a function of y, in the above one we have y is a function of x, but here we have x is a function of y. If we have given x as a function of y, we say the arc length from point A to point B is the integration. Here the only thing which changed from the above is the limits of the integration is from y0 to yn, but in the above it's from x0 to xn. Okay, and in the square root we have this is a function of x. We say we find dx by dy squared plus 1 dy. That's all. Here in the above one we took the integration with respect to x, but here we take the integration with respect to y, and y is from y0 to yn, and the derivative here which we have in the square root, it is dx by dy here, but in the above it is dy by dx, because in the above one the curve is y equals to f of x. Y is a function of x, but here x is a function of y. And if you have a function of xy, g of xy over the arc, over the curve, it equals to the integration from y0 to yn Here in the function, we have x and y. In the function g, we have x and y. We must have only one variable. Since we take the integration with respect to y, so we must have only y. But we have given that x is a function of y. So you replace x by f of y. That means here, if we replace x by f of y, we get only a function of y. That means it's a g of f of y and y. It's a function of y. We multiply it by the square root dy. We take the integration from y naught to yn. See, if the curve is given as parametric equations, that means if the curve is given as parametric equations, here we say x is f of t, y is h of t. In the previous chapter, we talked about parametric equations. We say x is f of t and y is h of t. If x is a function of t and y is a function of t, we say the arc length is the integration from t naught to tn. We take the integration with respect to t here. We take the integration with respect to t. df by dt, that means we take the integration, the derivative of x with respect to t, the function of x with respect to t, and the function of y with respect to t also. We take the square for both and then dt. And that's all. This is the arc length if you have given the parametric equation. Let's take an example for that one. If we have, let's say, the integration, if we have given that x to be, let's say, t squared and y to be 2t. Okay, then an ft between 0 to 1, let's say. Okay, then the arc length is the integration from t naught to tn. This is t naught, that's tn. The lower value of t is t naught, and the upper value is tn. This is from 0 to 1. Integration of the square root of df by dt, that means x prime. X prime is 2t plus 2t squared. Sorry, let's say it's t. Let's say that to be t. Okay. If it's t, then x prime is 1 squared plus y to be 2t. Its derivative is 2 dt. This equals the integration from 0 to 1. Here, 1 squared plus 2 squared is the square root of 5 dt. And this equals to the square root of 5t from 0 to 1. And this equals to square root of 5. This is the arc length from 0 to 1. If the parametric equations are t and 2t. It's like that. And if we have given a function of g of xy, here the arc length, the integration here, the integration of g of xy over the curve is g of f of t and h of t. We replace each x and y by t. How? Since we have given x and y, but by functions of t, we replace them in the function of t, and we get only g of t. Is it? Yeah. Let's say if g of xy to be 2xy. Okay. Then g of x of t, y of t, or g of f of t and h of t. It's the same as this. This equals to, we replace x by 2t, so x by t, and y by 2t. This equals to 2 times t times 2t, and this equals to 4t squared. This is g of x of t and y of t. We replace we substitute the parametric equations into the function of g of xy to get a function of t. And then we multiply it by derivative of f with respect to t squared plus derivative of h with respect to t squared in a squared, then dt. We take the integration for this formula from y naught to yn. From y naught to yn, or from x naught to xn, it's the same. We now have curve in xyz space. In the above one, we talked about curve on xy plane. We now have curve in xyz space. Say, given a curve C, this is the curve C. It is a vector value function, okay? It's a vector value function. R of t equals f of t I plus g of t j plus h of t k. Here, t is given that between t naught and tn. So these two t naught and tn becomes the limits of the integration, lower and upper limits for the integration. We say the arc length here, is the integration of the square root for derivative of all components squared, the sum of derivative for the components squared. We say the first component we find its derivative then squared. The second component we find its derivative then squared. The third component we find its derivative then squared. All in a square root. All in a square root. dt from t naught to tn. As you see here, we have only a function of t. We have only a function of t because f is a function of g is a function of t and h is a function of t. If we find the derivatives, it's still a function of t, and then squaring them is still a function of t. Okay, all together in a square root, it's a function of t then dt. So t is from t naught to tn. We find this integration, it will be the arc length for that curve. So from the above equation, from this equation here, we say r of t is f of t I plus g of t j plus h of t k. Then r prime of t equals, we find the derivative for each component. We talked about this before in the previous lecture, in the previous chapter. R prime of t is the derivative of all components. It is f prime of t I plus g prime of t j plus h prime of t k. Then to find the magnitude for r prime as the square root of, that is magnitude of a vector value function or vector as the squaring all components in a square root. Okay, squaring the first one is f prime squared plus second component is g prime squared plus h prime squared. As you see, this is the same as the square root which we have there. That means the arc length is the integration of magnitude of r prime from t naught to tn. So we can say this is the square root of magnitude of r prime. This is the magnitude of r prime. So the arc length here, if you have given a vector value function, the arc length is from t naught to tn for magnitude of r prime. And here we say if we take the derivative for both sides with respect to t, when we take the derivative for the right hand side, the integration is going to cancel out. Here dt, d by dt, I mean derivative for this by dt, this derivative with the integration are going to be cancelled out, so we get only the magnitude of r prime. And in the left hand side, if we take the integration, the derivative with respect to t, we get ds by dt. As you see, you got this one. Now we multiply both sides by dt, and we get ds equals the magnitude of r prime dt. So changing in the arc length as the magnitude of r prime dt. So the line integral in a scalar field, line integral as here we find the integration for this scalar field over the curve C. We say this integration equals the integration for the function. We replace each x, y, and z by their functions of t. X is a function of t, y is a function of t, and z is a function of t. Each of these is a parameter. They are parameters and they are functions of t. We say phi of f of t, g of t, and h of t times the square root of f prime squared plus g prime squared plus h prime squared, all dt. We find this integration over the curve C. We now have these rules that we use in solving the examples. Okay. All what I talked about are just rules. Okay. We now have line integrals in vector fields. Up to here, we talked about the line integrals for scalar fields and scalar fields. Now we have line integrals in vector fields. We say line integral of vector field f on curve C gives the value of work needed to move the object from initial point A to destination point B, moving on the given curve C. Here, line integral here, if we have, let's say this is the initial and this is the destination point. This is the curve. This is the curve from the initial point to the destination point. Line integral for vector fields over this curve is the work which needed for moving an object from this point to that point. Okay, it's the work we needed for moving an object from point A to point B over this curve. If you have curve like this, it's different. If you have curve like this, it's different. Okay, that means for different curves we get different works. We need different works. Line integrals in a plane, that means in xy space, xy plane. We say if the force is given by f of xy, which is p of xy I and q of xy j. This is the force. This is the force, which is the vector field. This is the vector field. And it's force also. And the curve C is given by a vector value function. We have given the curve by a vector value function. Then the work done is given by the following notation. Here, the work done is the integration over the curve for F, which is the force, dot dr. Here, we should find the derivative for R, or for R. Then we find the dot product of dr with F, with the force. Then find its integration. Here, if as it is given, R is xi plus yj. dr is the derivative for each component. Here we have two components, I component and j component. We find the derivative for each component. For the first component, it is dx, because derivative of x is dx and derivative of y is dy. You get this? Now we find this is dr. So dr is dxi plus dyj. If you find the dot product for dr with f equals p of xy I plus q of xy j. The dot product of these two here, we just multiply the first component by first component, then plus second component by second component. As the dot product of two vectors. See, we have two vectors, f and dr, both are vectors. Okay, we multiply p by dx plus q by dy. So we get p dx plus q dy. We find this integration. For p, we find with respect to x, and for q, we find with respect to y. Okay, over the curve C. This is the work done. We use this formula for finding work done if we have given the curve and the force. Here you have some important notes. Evaluating line integral on xy plane. After these notes, we have some examples that we solve. Okay, we have some rules, then we have some examples. We say after performing the dot product, I mean after doing this dot product, this is the result of the dot product of f and dr. After doing the dot product of f and dr, two situations must be considered. First, we say, are the initial point A and the destination point B given by Cartesian coordinates or given by parameters such as T0 and Tn? We must consider about this. If it's given as a Cartesian, that means it is x and y. This is x not y not, and that's x and y n. But if it's given as the parameters, it's T0 and Tn. It's T0 and Tn. So the limits of the integration is going to be changed. Is the curve given by this or this? Is the curve is given by y equals f of x or x equals h of y? Here, if the curve is given by this, we find the integration with respect to x. Okay, we must find the integration with respect to x. But if it is given as x to be a function of y, here we find the integration with respect to y. Okay. By the parametric equations, x is x of t, y is y of t, or it's given by, or the curve C is given by parametric equations. X is x of t and y of t. Here, in this case, we must find the integration with respect to t. Here, we must find the integration with respect to t. Or by a vector valued function, r of t equals x of ti plus y of tj. Here, it's the same as the above one. It's the same as the above one. This is x of t and this is y of t. So in this case, we find the integration with respect to t. So in the last two cases, we find the integration with respect to t, but in the above ones, here we find if we have given y equals a function of x as for the curve, we find the integration with respect to x. But if we have given x is a function of y, we find the integration with respect to y. We change all x to y, so we have no more we will have no x in the integration in this case. So we take the integration with respect to y, and here we change all y to x. and we get only x in the integration. We find the integration with respect to x. But in these two cases, we change all x and y by functions of t. So you just have t in the integration. We find with respect to t. You see, if c is given by this, if c is given by this here, we are going to write down, we have all the rules for these cases. For these cases, we say if y to be a function of x, then dy by dx is f prime of x, and the arc length is p of xy dx plus q of xy dy. Here, in this case, we must change all y to x. We must change all y to x. So this y becomes f of x. We replace f of x there. And here also we replace by f of x. But here we have dy. Here we have dy. But dy from this one, we can say dy is f prime of x dx. That means we can replace dy by f prime of x dx. Or we can say we multiply this by dx and dividing by dx. This, if we multiply it by dx and dividing by dx, here we get dy by dx times dx. So dy by dx is f prime. It's the same. We get the same. And here we use this rule. We use this rule if we have given y to be a function of x for the curve. If the curve is a function of x, we use this rule for finding the arc length. Okay. From x0 to xn, because the integration is with respect to x, we find the integration from x0 to x. Here, in this case, we must change all variables in integrals to become x. And we take x coordinate for the initial and destination points for the integral. That means lower and upper limits for the integration are the values of x. And here we have if the curve is a function of y. In this case, we change x to y. We change all x to y, and we change x by h of y. And here we say this integration, we replace x by h of y, this x by h of y. This is dy, it's okay. But we must change this to dy. How? We multiply it by dy and dividing by dy. So when we divide by dy, we get dx by dy. That means we find dx by dy from this one, which is h prime of y. And we get dx. So here, in this case, we use this formula for finding the arc length. We use this formula. Okay. P and Q are the components of the vector fields. So if C is given by a vector valued function, or if it's given by parameters, R of t is x of t and y of t, x of t I plus y of t j. So its components are x of t and y of t. So x is x of t, y is y of t. Hence, dx by dt is x prime of t. dy by dt is y prime of t. And we use this rule. We use this rule for finding the arc length. We said it's p of x of t, y of t. We replace each x by x of t, and we replace each y by y of t. And also here we have x prime dt. This is dx by dt times t. We multiply dx by dx and dividing by dx. And also we multiply dy by dt, then dividing by dt. So we get dx by dt, dt, and dy by dt, dt. Okay. we have this rule for finding the arc length if we have given parameters. If we have given parameters, but be careful here. The limits of the integration must be with respect to t. The limits of the integration are t naught and tn. So even if we have not given t, we must find it. We must find t. So now we have some examples. For the first example, as you see, it says evaluate the line integral, this one, where f of xy, it is the vector field, equals x cubed yi plus x minus yj, where c, the curve, is y equals x squared. Look, which of the above cases is this? It is y. Look, we have the curve which is a function of x. Y is x squared. It's a function of x. That means it is this case. This one is. As you see, y is a function of x. That means we use this formula for finding the arc length. Okay, we use this rule for finding the arc length. Why? Because the curve is given a function of x. Okay, so here, and the limits of the integration, here we have x naught, y naught, and xn, yn. Okay, here the limits of the integration are x naught and xn. We just take x naught and xn. That means it's from -2 to 1. We don't care about y values. Okay, because the limits of, we take the integration with respect to x. That means the limits for the integration must be x naught and xn. Must be x naught and xn. So they are -2 and 1. Let's first write down the information for this example here. We have given let me write down f of xy equals x cubed yi plus x minus y j, y equals x squared, and you have given that -2 to 4. It goes from this point to 1, 1. Okay, from this to that. Okay. Here we say the integration of f dot dr over curve C equals, look, this is the rule. This one is the rule. We find the integration with respect to x. We find the integration with respect to x, and we change all y to x in the integration. We say dr, the integration of f dot dr over the curve C is the integration from x naught to xn for p of xy dx plus q of xy dy. And now we have given p of xy and q of xy. Q of xy is the first component of the vector field. We say f of xy equals p of xy I plus q of xy j. That means p of xy is x cubed y, and q of xy is x minus y. Okay, the I component is P of xy, and J component is Q of xy. Here, we say it equals to, but we have given that y equals x squared. Y equals x squared. That means here P of xy is x cubed y. How about P of x and f of x? That means here we replace y by x squared. If we replace y by x squared, we get x to the power 5. Is it? We have x cubed times y. Y is x squared. That means x cubed times x squared, which is x to the power 5. This is P of x and f of x. How about Q? And Q of xy equals x minus y. How about Q of x and f of x? It's x minus x squared. Why do we change all variables to x? Because the curve is a function of x. As y equals x squared. But if x to be a function of y, in that case, we change all variables to y. Okay? That's it. Now, we need dy by dx also. Dy by dx equals 2x. This is y. So dy by dx is 2x. Then we say the integration equals from x0 to xn for P of x and f of x dx plus Q of x and f of x times dy by dx times dx. Why do you change dy to this? Look, here we have dy. We must have no y. We must have no y. To change dy, what we do? We multiply it by dx and divide it by dx. These two becomes dy by dx times dx. Okay, but we have dy by dx, which is the derivative of the curve. Derivative of the curve is dy by dx. Now we have dy by dx. We have Q of x and f of x and P of x and f of x. Now we replace them all here in the integration. Then we take the integration. How about x0 and xn? It's given that it's x0 and y0 to xn and yn. So x0 is -2 and xn is 1. We don't take the values of y because the integration is with respect to x. It's not with respect to y. Since we take the integration with respect to x, so we must take only the x values for the limits for the integration. This equals to the integration from -2 to 1. P of xy, P of x and f of x is x to the power 5. That's dx plus Q of x and f of x, which is x minus x squared times dy by dx, which is 2x dx. As you see, both terms include dx. So we just take dx as the common. That means we take the integration for both terms together. And this equals to the integration. Let's multiply this into the bracket from -2 to 1 for x to the power 5 plus 2x squared minus 2x cubed dx. We just multiply 2x by the brackets. Now we take the integration. It's easy to take this integration. It equals to x to the power 5 becomes x to the power 6 dividing by 6 plus x to the power 3 dividing by 3, and here we have 2 also, minus x to the power 4 dividing by 2 from, sorry? No. Integration and integral are the same. Okay, derivatives. We took the integration from -2 to 1. Now we replace x by 1. Then we replace x by -2. If we replace x by 1, what we get? We get 1 over 6 because 1 to the power 6 is still 6, is still 1. Plus 2 over 3 minus 1 over 2. Then minus. We replace x by -2. Since the exponent here is even, so it becomes positive. This is 64 over 6 plus here, since this exponent is odd, since that's odd, it's negative, so it becomes -8. -8 times 2 is -16, so this sign becomes -16 over 3. And since this exponent is even, it becomes positive, which is 16. And here we have a negative sign. We write down the same, -16 over 2. Now we just calculate this or simplify this. The left bracket here, the common denominator is 6. By this is 2, by this is 3. We multiply these two above. Okay, we multiply this 2 and 3 to above. We get 4 minus 3 plus 1, which is 2 over 6. Yeah, that's 2 over 6 minus. For this one, the common denominator is 6. By this one is 2, by this one is 3. Multiply them two above. We get 64. 2 times 16 is 32. And 3 times 16 is 48. All dividing by 6. This is minus. Minus 32 and minus 48 is -80. -80 plus 64 is -16. And here you have this negative sign, it becomes +16. Okay, that's 16 over 6. This equals to 3. So the arc length is 3 because 18 over 6 is 3. The arc length for this example is 3, from -2 to 1, that is 3. Okay. Look, y equals x squared is like this. -2 and 4, -2 and 4. This is -2 and 4. This is 1, 1. So this length is 3. It's 3 units. Okay. It's that length. This is 3. It's arc length. Let's take a break. Okay. Let's take a break for 10 minutes. We now have another example. In this example, it says evaluate the line integral. It says evaluate the line integral f dot dr, where the vector field is given by this, and the curve C is given by x equals 2t and y equals t squared. Here we have given the curve as set of equations of parameters. X is 2t and y is t squared. From this point to that point. Here, these 2 points that we have are x naught, y naught, xn, and yn. Let's turn to above. We said if you have given the curve as a set of parameters, x equals x of t and y equals y of t. We use this rule. For finding the line integral. The rule is the integration from t naught to tn. But in the example we have given x naught xn, y naught yn, x naught y naught xn yn. But we must find x naught, t naught and tn. It's p of x of t, y of t. We must replace x by x of t and y by y of t in p of xy. Multiplying by dx by dt, then dt. Q of x of t, y of t, dy by dt, dt. Let's see. Let's write down the information here. The vector field is f of xy equals 3xy I b. F of xy is 3xyi minus y squared j and we also have given the curve as x equals 2t and y equals t squared. And we also have given the initial and destination points, which are 0, 0 to 4, 4. Okay, we have given these. As we have in above, we said if we have given the curve, these are the curve. Curve C. We have given the curve as a set of parameters. We say we use this rule for finding the line integral. It's the integration from t naught to tn for p of x of t, y of t, dx by dt, dt, plus q of x of t, y of t, dy by dt, dt. Okay, we should first find t naught, tn, p of x of t, y of t, q of x of t, y of t, and also dx by dt, dy by dt. These are x and y. From these two, we can get the dx by dt and dy by dt. We say dx by dt equals 2 and dy by dt equals 2t. From the parametric equations, we can get dx by dt and dy by dt. And also, we should find p of x of t, y of t. P of xy equals to what? We have given this vector field. From the vector field, the I component is p of xy, and j component is q of xy. So p of xy is 3xy. So p of x of t and y of t is, we replace x by 2t and y by t squared. We have given that. We have given that x is 2t and y of t, y is t squared. We replace x by 2t and y by t squared. We get 3 times 2 is 6 t cubed. This is p of x of t, y of t. Okay, And also we find q of, here we have given that q of xy is minus y squared. It's minus y squared. Then q of x of t, y of t equals, we replace y by t squared, and you get minus t to the power 4. These two are q of x of ty of t and q of x of ty of t. And you also need to find t naught and tn. How to find t naught and tn? We have given that x is 2t. X is 2t. We give x naught and xn to this to get t naught and tn. Okay, here x naught is 0. So t naught is 0 also, because if we replace x by 0, we get 2t equals 0, so t is 0. That means t naught is 0. And xn is 4. If we replace x by 4 here, if we replace x by 4, we get 2t equals 4, so t is 2. Tn is 2. That means t naught is 0 and tn is 2. So t is between 0 and 2. ليه x أنا بدو t y x أنا بدو t squared. هاي كم يكون ورقة كشني أبيها ما أشتغل ده شيء. باشا دين شيء x دراو أما x نقطة أما y نقطة أما x أنا أما y أنا x نقطة y x نقطة x n ورقة يعني y نقطة y n ورقة لو y كذا عنده كشني أما x كم ورقة x كات دو t x دو t بيت x أنا بدو t كواتر أجر x صفر بيت x نقطة كمان صفر. We get t naught in this case. Okay, if we replace x by 0, we get 2t. 2t equals 0, so t is 0. That means t naught is 0. Okay, and if x to be 4, xn is 4. Xn is 4. If we replace here x by 4, we get 2t equals 2t. So t is 2. That's why we say t is from 0 to 2. So t naught is 0 and tn is 2. Even for y, if we do, we get the same. Even if we take y to be t squared, y is from 0 to 4. Y is from 0 to 4. We replace y by 0, then y by 4. We get the same. We get that t naught is 0 and tn is 2. Now, we replace q of x of t, y of t, dx by dt, q of x of t, y of t, and dy by dt. And also t naught and tn here. We get the integration from 0 to 2. Q of x of t, y of t is 60 cubed. Dx by dt is 2. This is dt plus q of x of t, y of t is minus t to the power 4 times dy by dt is 2t dt. We find this integration. This equals to, let's first simplify it. From 0 to 2, it is 12t cubed minus 2t to the power 5 all dt. Because both are dt, we just take dt for both. Now we take the integration with respect to t. This equals to integration for the first term is t to the power 4 over 4. 4 in the denominator is going to cancel out with 12. We get 3t to the power 4. Okay, we get 12t to the power 4 dividing by 4, and we cancel out the denominator with 12. We get 3t to the power 4 and minus t to the power 6 over 3 from 0 to 2. We replace t by 2 first, then by 0. If we replace by 2, we get 3 times 16 minus 64 over 3 minus 0. If we replace t by 0, we get 0. And this equals to 3 times 16 is 48. 48 minus 64 over 3. This equals to 3 times 48 is 144. 144. We find a common denominator. This equals to 80 over 3. It is 80 over 3. Okay. It's 26.66 like that. This is the line integral for the second example. Okay. It's easy. If you just know the rules here, we just use these rules. We just use these 3 rules. In the third example, we have the vector field in XYZ space. It's f of x, y, z. Here you have 3 components, I, j, and k. You have 3 components. And we have given that r of t equals t squared I plus 2tj plus tk. In this case, it is similar to the previous one. It's similar to the second example. Here, t squared is x of t. 2t is y of t. And t is z of t. Okay, we have 3 components. So x of t is t squared, y of t is 2t, and z of t is t. That's the same as the previous example. We do the same. Let's first write down the information here. F of x, y, z equals y squared minus z squared I, c. I minus 2yzj plus x squared k, yeah, plus x squared k. And you have given that the curve is r of t equals t squared I plus 2tj plus tk. This is curve. The curve is given as a parametric equation. And it says from 0, 0, 0 to 1, 2, 1. This is x naught, y naught, z naught. This xn, yn, zn. Here, the curve is given as an equation of parametric. It is a parametric equation. From the curve, we can get that x of t is t squared, y of t is 2t, and z of t is t. We now do the same as we did before in the previous example. We should find p of x of t, y of t, z of t, q of x of t, y of t, z of t, and r of x of t, y of t, z of t. Okay, here this is p, this is q, and this one is r. Okay, we name it by r. We say the line integral is equal to x naught, so t naught to tn, t naught to tn, for p of x of t, y of t, z of t, dx by dt dt, plus q of x of t, y of t, z of t, dy by dt plus r of x of t, y of t, z of t, dz by dt. So here we should find P, Q, and R as equations of t. And also we should find dx by dt, dy by dt, dz by dt. And also we are going to find t naught and tn. Let's find them all. Here, P of x of t, y of t, z of t equals to what? P is this function. This is P of x, y, z. We replace x by t squared, y by 2t, and z by t. Let's do it here. This is P. P equals y squared minus z squared. If we replace y by 2t and z by t, we get 4t squared minus t squared. Okay? We get 4t squared minus t squared. And this equals to 3t squared. This is P of x of t, y of t, z. And then for Q, Q of x of t, y of t, z of t equals. This is Q. Q is minus 2yz. We replace y by 2t and z by t. As you see, y is 2t and z is t. We replace y by 2t and z by t. We get 4t squared minus 4t squared. Because it's negative. This one, Q is negative, minus 2yz. And for R, R is x squared. If we replace x by t squared, we get t to the power 4. R of x of t, y of t, z of t equals t to the power 4. Now, we have P, Q, and R for t. And also you should find dx by dt, this is x. So dx by dt is 2t. dy by dt is 2 because y is 2t. And dz by dt equals 1 because z is t. This is 1. And now we should find x t naught and tn, t naught and tn. So you can take any of x naught xn or y naught yn or z naught zn. You can take any of them. You must get the same value for t. Okay, let's take y. Let's take y. Y naught is 0 and yn is 2. So from these two, since y equals 2t, if we replace y by 0, so t is 0. So t naught is 0. And if we replace y by 2, we get t is 1. That means t is from 0 to 1. If someone else take x, okay? So x is from 0 to 1. And x is t squared. It's x naught and then xn. If we replace x naught, if we replace x by x naught, which is 0, we get 0. So t naught is 0. And if we replace it by 1, we get 1. Even for z, the same. We get the same value at each case. So we now have all the required information. Now we say this equals to the integration from 0 to 1. That means t is from 0 to 1. P of x of t, y of t, z of t is 3t squared. Then multiplying by dx by dt. Dx by dt is 2t minus 4t squared. I'm just going to write down dt for all, because all are dt, all terms are dt, we get dt for all. We will write down dt for all. 4t squared times dy by dt. dy by dt is 2. Then plus t to the power 4, sorry, multiplying by 1. All dt. And this equals to the integration from 0 to 1. Let's first simplify it. We get 60 to the power 4. Yeah, sorry, cubed. T squared times is t cubed. Minus 8t squared plus t to the power 4. Now we take the integration. So the integration is t to the power 4 over 4, which is 3 over 2 t to the power 4. Okay, minus 8 over 3 t to the power 3. Plus t to the power 5 over 5 from 0 to 1. First, we replace t by 1. We get 3 over 2 minus 8 over 3 plus 1 over 5. Then we replace by 0 minus 0. This equals to 3 over 2. Here we take the common denominator, which is 15. No, it's 30. 30 is the common denominator, 30. Dividing by this is 15. This is 10. This is 6. We multiply it up, we get 15 times 3 is 45 minus 80 plus 6 dividing by 30. This equals to it's 15, it's negative 29. This is the line integral. This is the line integral. Okay, that's it. So the most important thing here is to recognize the example, recognize the question. If you know which of these 3 rules do you use, it's easy. Okay, it's easy to calculate it. Okay, it's enough for today.